You ever stop to think about how the box that just landed on your doorstep and the can of soda in your fridge have something absolutely incredible in common? It's that they both started life as a completely flat piece of material. So today, we're going to unfold the secret of how that amazing transformation happens. We're diving into the hidden blueprints that literally shape our world. Okay, let's jump right in. Imagine your favorite energy drink is launching a brand new flavor. Now, before they can make millions of cans, someone, somewhere, has to design the perfect flat pattern that gets cut, printed, and folded. If you get it wrong, you've got a leaky, useless mess. But if you get it right, you have a perfect package. So what's the secret? Well, the answer lies in this really brilliant geometric concept called a net. You can think of a net as the 2D master plan. It's the flat pattern that, when you fold it in just the right places, magically transforms into a 3D object. It is the absolute key to turning a sheet of cardboard into a box. And the cool thing is, you already know how this works, intuitively. Just picture an empty tissue box. If you were to carefully cut along its edges and just lay it out completely flat on a table, what you're looking at is its net. You've just deconstructed the box right back to its original 2D blueprint. Now, for any of this to work, there is one single, non-negotiable golden rule. Any two edges that are supposed to join together when you fold the shape up have to be the exact same length. If they're not, even by a tiny bit, the shape just won't close right. It's the fundamental law of nets. So, with that one crucial rule in our back pocket, let's take a look at the specific blueprints for some of the most common shapes that we see every single day. Let's kick things off with a classic, the cube. A cube has 6 identical square faces, right? So its net has to have 6 squares. But here's a little puzzle for you. Can you just arrange those 6 squares any way you want and expect it to fold up into a perfect cube? What do you think? Well, let's put it to the test. If you look at these 4 different arrangements, you might think they'd all work. They all have 6 squares. But when you actually try to fold them up in your mind, you realize that only figures 1 and 3 actually make a proper cube. The other 2, they totally fail. So the big question is, why do they fail? Well, it usually comes down to 2 simple problems. In some cases, like figure 2, the squares are laid out in a way that causes 2 of them to fold over and land on the exact same face. They overlap. In others, like figure 4, the pattern leaves a big old gap. One face is left with no partner to fold against, so you literally can't close the box. This shows us that the arrangement is just as important as the shapes themselves. Okay, so let's apply this to probably the most common 3D shape out there, the rectangular prism. And that's just a fancy name for any object where all 6 faces are rectangles. Like a brick, a shoebox, or that tissue box we were just talking about. So if you were the one designing the net for this tissue box, you think about it logically. You'd probably start with the bottom, then you'd attach the front and back walls, then the 2 side walls, and then finally you'd slap the top on. The whole key is that every piece connects, and every single edge that's going to be joined has a perfectly matching partner. It's like a little engineering puzzle. Now, to understand some other really common shapes, we need one more quick concept. It's called the cross-section. The easiest way to think about it is to imagine slicing a loaf of bread. Every single slice has the exact same rectangular shape, right? Well, that repeating shape, that is the cross-section. And this is basically the secret decoder for identifying different types of prisms. If the cross-section is a rectangle, you've got a rectangular prism. If you slice it and see a triangle, it's a triangular prism. And if that cross-section is a perfect circle, well, then you're looking at a cylinder. The cross-section tells you everything. So let's take a triangular prism. Think of a tent, or maybe a wedge of cheese. Its blueprint is made of 2 identical triangles for the ends, and 3 rectangles that wrap around to form the sides. And of course, that golden rule is in full effect. The width of each of those rectangles has to perfectly match the length of the triangle edge it's attached to. If it doesn't, your tent is going to have a gop. But now we get to what is, I think, the most elegant and surprising blueprint of all, the cylinder. This is one of those real aha moments in geometry, where a curved object reveals a secret that is just beautifully simple. Okay, so a cylinder obviously has 2 circular faces, a top and a bottom. That part's easy. But what about that single, continuous, curved surface that connects them? What do you think that looks like when you unroll it and lay it flat? It becomes a perfect rectangle. And this, right here, leads to the most important engineering question you could ask. How long does that rectangle need to be? Because if you make it too short, the can's going to have a gap. If you make it too long, it's going to overlap. For that can to seal perfectly, the length has to be exact. The answer is one of the most famous and powerful little formulas in all of mathematics. The length of that rectangle must be exactly pi times the diameter of its circular base. And when you stop and think about it, it makes perfect sense, right? The length of that rectangle has to be just long enough to wrap perfectly one single time around the edge of the circular top. And what do we call the distance around a circle? Its circumference, which is always, beautifully, pi times its diameter. So let's put that into practice. For a normal can of soup with, say, a 6-centimeter diameter, the flat piece of metal that forms its side needs to be cut to exactly 18.84 centimeters long. There's no guesswork. It's just pure, precise math making it all work. So, this is all fascinating geometry, for sure. But why does it really matter? Well, because these blueprints, these nets, are absolutely everywhere, hiding in plain sight. I mean, from the obvious stuff like all the packaging we see, to massive industrial manufacturing, and even in things like temporary pop-up displays for events, the simple logic of nets is the foundation that lets us build things efficiently. I mean, really think about it. Every single Amazon box you get is cut from a net that's been designed to create the absolute minimum amount of waste. That pi times d formula isn't just for a textbook, it is used to manufacture millions of cans and pipes with perfect seams every single day. And those wedge-shaped display ramps you see at a store, they're just giant folded-up nets of triangular prisms. So, the big takeaway here is this. From these simple, flat patterns, our entire 3D world is constructed. Nets really are the secret blueprints behind the objects we use every day without a second thought. And that leaves me with one final thought for you. Now that you can see these blueprints hiding everywhere, what other hidden patterns are out there, quietly shaping the world all around you?